Hi, this is Mr. D. Crane again, and I'm continuing my video series on linear programming. So this is Linear Programming Part 2, Evaluating the Objective Function. In Part 1, we looked at this problem exactly, and we discovered that the feasible region, in other words, the region that made all of these inequalities true, is the one that I've highlighted in blue on the graph. What I want to do now is talk about the objective function and what that tells us and what we can figure out from this feasible region. So first of all, the objective function is usually something in terms of x and y, but it doesn't have a particular value associated with it. Like the constraints that we graphed already had x's and y's, but they had some sort of thing. We wanted x plus y to be less than or equal to 15 or something like that. For an objective function, we've got 5x plus 3y, and we don't know exactly what it's equal to, and the idea is to figure out what values are possible. So what we want to do is look at a point and pick any point in the feasible region. Let's pick this one right here. Let's see, that's going to be 2, 11. And at 2, 11, the objective function, the value would be 5 times 2 plus 3 times 11. So the value would be 10 plus 33, which is 43. Here's the thing, depending on which point I pick, I can get different values for that objective function. So if I pick this one, for example, that's, what is that, 1, 5, 6, 7, 8, 1, 8, the value would be, oops, not 5, sorry. It should be 5 times 1 plus 3 times 8. So the value would be 5 plus 24. The value would be 29. So even though it's not far away from 2, 11, you can see it's got a very different value. So you might ask yourself, okay, so what's the biggest value I can possibly get? Or what's the smallest value we can possibly get? In an actual linear programming problem, the objective function may correspond to the profit you can make by selling something. It might correspond to the cost it takes to make something. Maybe it'll correspond to the number of things you can actually make. And you want to know what's the maximum and what's the minimum values for those. Now, it turns out that the objective function gets its maximum and minimum values at the corners. So I've got to think about the corners of my feasible region, because that's where the maximum and minimum values are. And I can identify these pretty easily from the graph. On some other problems, we sometimes have to solve a system of equations to get these. But the point here is going to be, let's see, that's 1, 2, 3, 4, 11. This point up here is 0, 15. This guy here is 1, 5, and this guy here is 0, 5. And so what I want to do is find the value of my objective function at all 4 of those points, because those are the key points that are going to have maximum and minimum. There may be some other values in there, but the maximum will definitely be at one of those points, and the minimum will definitely be at one of those points. So we're going to call these our corners or vertices. And I'm just going to list them here. 0, 5, 1, 5, 4, 11, and 0, 15. And I want to evaluate that objective function for each one of these. So at 0, 5, my value is going to be 5 times 0 plus 3 times 5. So my value is going to be 0 plus 15. That's 15. At 1, 5, my value, again, I'm going back, I'm just plugging in values for x and y from those corners. 5 times 1 plus 3 times 5 is going to give me 5 plus 15, that's 20. Here, the value is going to be 5 times 4 plus 3 times 11. Let's see, that's going to be 20 plus 33, that's going to be 53. And here, my value is going to be 5 times 0 plus 3 times 15. That's going to be 45. So we get a number of different values, but here's the thing. The biggest of those is 53. So 4, 11 is the point where the objective function is maximized. And the smallest one of those, 15, comes from 0, 5, and that's where the objective function is minimized. So always at the corners, at the vertices of that feasible region, we can find the minimum value of the objective function and the maximum value of the objective function, and the coordinates that get us there. That's all we're doing with that. That's where we find minimums and maximums. So anywhere at any point I pick in this region, when I evaluate the objective function at that point, it's going to be something between 15 and 53. It will never go outside those boundaries. For those of you paying attention to functions, the objective function is indeed a function, and we say the value in this particular case equals 5x plus 3y. I want you to notice something. Our input is an ordered pair, x comma y, and the domain is any point in the feasible region. The output is some value, and the range is a number between 15 and 53. So that's kind of an aside, kind of connecting that back to our domain and range discussion earlier. The important idea here is that when you're given a set of constraints and you find the feasible region based on those constraints, once you find the corners, the vertices of that feasible region, you can evaluate the objective function, and one of those is going to be the minimum and one of those is going to be the maximum. And for a regular word problem that we're going to be looking at in part 3 of this video, we often want to know what's the minimum value. For example, what's the minimum cost we'll have to pay, or what's the maximum profit we can make. So that's why those points are going to be important. Hopefully this helps. Enjoy. Have a good day.